All right, so anytime that we're looking at bases, we're going to be using the Kb values. So remember, with acids, you use Ka, bases, you're going to use Kb. So we want to calculate the Kb value of a 0.1 molar solution of a weak base with a hydroxide concentration of this. Okay, so in order to calculate Kb, we need the concentrations of all the components. So we need to write out an equation. So a weak base, you don't know what it is. It really doesn't matter because remember, you're just moving a hydrogen around. Plus water will always make, well, if it's a base, it's going to make hydroxide, and then some conjugate acid, whatever this is, plus a hydrogen will give you a conjugate acid. All right, so in order to get Kb, I need the concentration of hydroxide, which I do have, plus the concentration of the conjugate acid divided by the concentration of my weak base. And of course we don't include the water. So we need to do an ice table. Alright, so water doesn't matter, but the weak base has an initial concentration of 0.1, and initially the hydroxide concentration was 0, so was the conjugate acid. Well, we have 0 for products, so we're going to be adding our products and subtracting for our reactants. Well, it tells us what the concentration of hydroxide is, so let's just go ahead and put that down. We know that the concentration is equal to this. Well, I know that I'm going to have equal parts of hydroxide and my conjugate acid, so I already know what the concentration of the acid should be too. Well, for the weak base, it's going to be 0.1 minus x, so 0.1 minus 1.75 times 10 to the negative third. Well, I have all of my concentrations at equilibrium, so now I can just simply plug it into the Kb expression and solve. All right, so Kb is equal to this. Times this. Divided by 0.1 minus this. All right, so when I go through and I solve for Kb, I will get 3.11 times 10 to the negative fifth. All right, so now let's look at the next one. All right, so calculate the Kb of a solution with 0.25 moles per liter of a weak base with a pH of 9.12. Okay, so this is very similar to the last one, except they give us the pH and not the hydroxide concentration. So let's go ahead and let's write out our equation first. Our weak base plus water will give us hydroxide and the conjugate acid. Well, let's go ahead and draw out our ice table. Our initial concentration of the weak base is 0.25. Hydroxide 0, conjugate acid is 0, and I'll be adding for my products, subtracting for my reactants. Okay, so now it does not give us a hydroxide concentration, but it does tell us the pH. So we do have some information here. So when I'm looking at pH, I can get my hydroxide concentration from this. Now, if I've just simply solved for the concentration here, I'm going to get the concentration of hydronium, which is not included here. So I need to get the hydroxide concentration, and I can do that by finding the pOH, because pH plus pOH is going to be 14. So 9.12 subtracted from 14 would give me a pOH of 4.88. All right, so now that I've got that, I need to solve for my hydroxide concentration, because my pOH is equal to the negative log of the concentration of hydroxide. So POH is 4.88. That's equal to the negative log of the hydroxide. All right, so move the negative sign over. Do the opposite of a log, which is 10 to some power. And my hydroxide concentration should be 1.32 times 10 to the negative fifth. All right, so I do have my hydroxide concentration then. So that's going to be equal to X. So it's 1.32 times 10 to the negative fifth. Same thing for the conjugate acid. And then for my weak base, it's going to be 0.25 minus that number. All right, so now I'll just simply plug it into the Kb expression. So 1.32 times 10 to the negative fifth, multiplied by the same thing, so basically squared, divided by this. All right, so Kb, when I solve for it, I should get 6.95 times 10 to the 10th, negative 10th. All right, so let's do one more. All right, so what is the pH of a 0.44 molar solution of ammonia? And it gives us the Kb. And then what are the concentrations of each of the species? All right, so we have ammonia, and we've put it into water. So remember, anytime we're just looking at a weak base or a weak acid, we're just putting it into water. So it's a base, so that means that the hydrogen gets transferred to the base. So it becomes ammonium and then hydroxide. So when I do this, let's go ahead and set up an ice table. So the initial concentration of the ammonia is 0.44. 0 for ammonium and hydroxide. Well, we're adding products and subtracting reactants. All right, so now it gives us the Kb value here. So what we're going to do is we're going to find the concentrations of everything, and then we're going to solve for pH. So to get pH, I need the concentration of hydronium, or I need the POH, because I know that the sum of the pH and the POH is 14. Well, since we're looking at a base here, since I'm looking at a base, I am going to look at hydroxide. So I need to get the concentration. I need to find out what X is. So let's put it into the Kb expression. So Kb is equal to this, which is equal to my products over my reactants. So X times X divided by 0.44 minus X. Well, this number is very small, so I can use approximation. I can get rid of that X. So I really just have X times X divided by 0.44. All right, so then I'm going to go through 1.8 times 10 to the negative fifth is equal to X squared divided by 0.44. Let's get rid of the 0.44. All right, so when we do that, when I go through and I finally solve for the X, X is going to be equal to 0.0028. All right, so that means that I have the concentration of the hydroxide, which is 0.0028. I have X. I also have ammonium because they're equal to each other. And then this would be 0.44 minus 0.0028, which would be 0.4373. So I have this, I have this, I have the concentrations of everything. Now I just need to do the last thing and get the pH. So I know the hydroxide concentration. I can solve for the POH first. POH is equal to the negative log of the concentration of hydroxide. So when I solve for that, I am going to get 2.55. So then subtract this from 14 and my pH should be 11.45. So when you're solving for this, if you get a pH that doesn't seem right, so if you have a base, it should be above 7. If you have an acid, it should be below 7. If you get something that's the opposite, you've probably solved for POH or pH instead of the opposite. All right.